Hello, hello. Hello, everybody. How are you today? Hi,
Hello,
Marcos.
hello, Chema. How are you doing?
I'm doing well. It looks like you are a little bit different than Ellie.
Yeah, just a bit.
So yeah, Ellie, probably um, you know her because she usually connect to these webinars. She had a bad night. She has to recover herself. She's not feeling very well. So we have Marcos. Probably all of you know Marcos. He's one of our best engineers in Frenetic, and he has a lot of experience also in the full bridge phase shift. So welcome, Marcos, to the show.
Perfect, perfect. I'm very excited to see how it's look like. So let's
Okay,
go.
so today we will talk about full bridge phase shift, and I will explain some specific details that are interesting to be considered. Um, but before starting, I would like to talk a little bit about when it's common to use this converter. So, so when you are working at very, very low power, so you have an auxiliary power supply, or you are doing I don't know, 50 watt, 40 watt, 100 watt maximum. Most of those cases, you will be using a flyback. Um, but once the power is a little bit higher, above 100 watts, flybacks become so inefficient, and you want to have 90 plus 92 93% of efficiency, and then the most popular solution is phase shift full bridge. um, the maximum power I have seen full bridge phase shift, to be honest, I think I have seen even unto 10 kilowatt, but I would say maybe 5 or 6 kilowatt is very, let's say, where from 100 to 300 watt to 5 kilowatt is a very optimal space for a full bridge phase shift. But I don't know, Marcos, you have been working in a few of them. What's your experience in terms of power levels?
Yeah, typically are in the range that you are commented because to more power, the limitation are the semiconductors basically. So you need another topologies, okay. But I also see that with silicon carbides, MOSFETs, and so on, good control techniques, you can go up to 10, even 20 kilowatts. So yeah, for example, I did a phase full bridge in the past for a resistant hotspot welder, and the power. It's true that this was instantaneous power, but it was up to 20 kilowatts, and I used the phase full bridge to control the output power. So yeah, I think it should be fine operating at these levels.
Yeah, super interesting. So what you're saying also is that in some pulsating converters, when you just need a peak of energy, for a few instance, full bridge can work. And I always have this doubt, or people is asking me like, hey, and when you have a peak, so you have a peak, and the converter is going to operate in that peak for for a few, let's say, milliseconds. How do you size the components? Well, in voltage, I understand. Let's say you go to the semiconductors and say like maximum voltage of the peak. You cannot break the semiconductors. But for example, for the transformer, what do you need to know to avoid that everything explodes when you're just working on that kind of peak point?
Well, for the transformer point of view, it is very important to know the thermal behavior of the transformer and the thermal. Let's say when you're starting to apply power to a transformer, the temperature start to rise. until you reach the steady state temperature, okay? But this behavior is not something that is instantaneously. So it takes like 1 hour, 2 hours to reach the maximum hotspot. So if you can guarantee that during the peak, depending also of the repetitivity of the peaks, okay? Because you can have one peak of 1 millisecond, but if you have 10 peaks or 100 peaks in 1 second, it's most similar to the steady state, okay? So it depends on these conditions. Yes, basically you need to guarantee that when you are in the peak, the temperature is not rising until you reach the Curie temperature or the limit of the temperature for the copper on or the plastics parts of the transformer.
Okay, so looks very interesting. So with that, maybe for another specific webinar, we can talk and study this, let's say, the behavioral of the temperature in terms of how is the slope of the temperature for each component, and how to play with the different type of heat sinks or heat dissipation techniques, because if we will be able to control that the slope for this type of converters like welding machines or lasers or things like that, the design could be much more optimized, and you don't need like a big box, even if you are delivering big currents of thousands of amps.
Yeah, so true.
Okay, so so now let's start with the slides I have prepared. So so let me know if you can see my screen.
Yep.
Can you see my screen? Yeah. Okay. 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 So today we are going to talk. Well, I'm going to make a brief introduction about what these products and this company doing, Frenetic, for all of you that are not familiar. Also, you will see some pricing things. And we will talk about this full refresh chef. Just not a basic. First, we will do a basic design, and then we will move to analyzing what is happening when you have, let's say, to increase the zero voltage switching range. So let's do it. So first, what are the Frenetic products? So let me explain how is our platform. So we have two sides. One is the Frenetic AI, and then we have Frenetic Simulator. Frenetic AI is the assistant that it will help you to design the converter, and every time we are adding more capabilities, it's more like an AI assistant. So it's going to help you to run simulations, build, let's say, create projects in other softwares like LTSpice, Plex, or even their own Frenetic simulator, and even just doing adjustments in the design of the converter. In the near future, also, you will be able to manage bill of materials, planar magnetics, and things that are coming very soon. In the Frenetic simulator is the way, let's say, is the most accurate way to have predictions about the losses and the temperature in a magnetic. And we have a lot of resources in our website where you can see the, let's say, the accuracy of the simulations, especially for measurement temperatures, electrical parameters. So there are like a lot of information that could be relevant for you to understand this. So now let's jump directly to this demo of how to design and build this basic full refresh chef. So let me now move to the browser. This is when you come to Frenetic AI, our website, you can just click here. This is you can try this for free. You have up to 8 credits. So you can click here, create an account, and you will have this. So if you are watching this and you don't have an account, I really invite you to test this right now. It's going to be for free, so you can follow what I'm doing. So I'm going to choose this crazy full bridge, and I'm going to start with the specs for today. That is a 270 volts input, 48 volts output and 2 kilowatt. So since these use AI, so you can write this in any format you want. So there is no any way, let's say, any bad way. So and even if you want to add additional requirements. So, but this is the basic. So now what I just run, and then the system is just looking for a specific design. So there we go. So you can see now the magic has happened, and we have a design for this full bridge shape. So actually, by recommendation of our friend Ben Jacob, we have included a little bit more detail in the drawings about the importance of the coupling factor for the transformer. I can explain this in a minute, but let me go through what is the system generating. So right now here, the system is choosing a frequency. You can suggest or fix your own frequency, but if you don't say anything for this 2 kilowatt, the system chooses a 100 kilohertz frequency. It chooses also the output inductance, 14 microhenries, and now for these operating conditions, it's calculating what is going to be the duty cycle needed for getting 48 volts and 270 volts for a specific tune radio. And what is the tune radio? Here we can see the tune radio in the transformer, and also what is the magnetizing inductance. So here you cannot see, but as you have been in other webinars, so also we have some tools that if you are really interested, I can give you access that are for calculating the zero voltage switching for this converter. If you know your parasitic capacitance of your semiconductors, and to be more accurate, you will need also the parasitic capacitance of the transformer. So now I'm asking the system to create a project for create the magnetics and create the projects for studying the magnetics. So there we go. Here we already have the design of the transformer. So you can see that now we have designed the transformer, let's say for these conditions, and we can see the specs. So here is like a total losses is 10 watts for these 2 kilowatts. So I think is reasonable. We have a maximum temperature of 100 degrees. If you want to have something lower, also you can specify in the design requirements here. And this is the size. So now I can click on open the magnetic simulator and see that. But before, I'm going to download the LT Spice, because this is going to be interesting for the next part of the, for the second part of the discussion that is about the simulation. So click and download. So I just download the file. Let me show it to you. So this is the file I just download. I can open it. You see, this is the full refresh shift. You can run it. And there you go. You have automatically the waveforms here for this case. And if you want now, I mean, the next part is to analyze this in detail. I can open the details of this transformer. So our AI has created the complete project, as you can see. So automatically it has created the project. It has fulfilled all the information needed, and also has selected the core, the margin type for the isolation due to the voltage, and here also you can see the details of the windings. So if you register Frenetic AI, so you have access to this during one day. So during one day, you can test your designs or your ideas here. So you can see how to get benefit of this technology. Something interesting to see is that the design is suggested is a E42 core, but with 2 stacks. So if you want to test new options, always you can come here and ask to suggest more designs, let's say 3, and we will generate the system will generate different designs for you. Or if you are more specific and you have more experience, you can come up to our code optimizer and try to look for your, let's say, optimal design, maybe just searching for what is going to be for a specific core, let's say BTD 49 or maybe better 49, like this one. And then you can see how is the core losses against the number of terms for keeping the magnetizing inductance that we want. So you can see here the power density and the maximum magnetic flux and the core losses. So you can play with this. This is generating new designs. We will let this go in. So that's all for, let's say, this automatic generation of the full bridge shift and magnetic. As you have seen, I have created a complete project in, let's say, I think it's been 7 minutes. Now we can go to more detail to analyze what is, let's say, different conditions and see, for example, what we were commenting in the previous with Marcos about, okay, what's happening if I have a peak of 3 kilowatts? So you can come here, create a new operating condition like this one, and try to say, hey, what's happened to this magnetic is I apply 3 kilowatts, so instead of 2. So you can see like now the temperature is rising, and you can, let's say, we can compare 2 conditions and see like, okay, for this case, we have increased the losses in the mainly in the winding from 3.5 to 8.3, would make sense. A little bit in the core, but probably is just because temperature rise. And we have here the final temperature. So it's a good way to have an overview of all the operating conditions for your converter and your magnetic. So now let's come back to the discussion about the leading leg and the lagging leg. So here, when you have the converter, there is something very important to have a full bridge shift. It's like you need to have zero voltage switching. And zero voltage switching means that you are going to reduce the losses in each switching cycle for each semiconductor, each MOSFET or whatever technology you are using. But let's think that is a MOSFET. And what you are, the way to have zero voltage switching is to discharge the parasitic capacitance of each component as fast as you can, or let's say before the next signal to switch on that MOSFET. You don't want to have voltage and current at the same time in each semiconductor. So one of the, let's say, best ways to do this is to use the leakage inductance to discharge in this dead time the transistors. But when you are working, as I was showing you before in the calculations, if you're working in a case where the tune rate is very high, or let's say the relations of the leakage inductance maybe is not, let's say, optimal, some cases you need to add an external inductor. So this external inductor is going to give you more range of leakage, let's say, of zero voltage switching in the lighter loads. I mean, when you have less power, you are delivering less power. So, so if you add an additional inductor here, it's likely that you are going to have high oscillations in the transformer due to the relation between this inductance, and the parasitic capacitance of the so between these inductance together with this and the parasitic capacitance here, together with other values. But these three components are the ones that are going to resonate, and then you will have some oscillations here in the transformer. So to avoid that oscillations to break any MOSFET or to have any problem, we can fix the voltage with these two clamping diodes. So these clamping diodes, what are doing is when the voltage starts oscillating, it the voltage at some point, at some value, and then you don't have this, let's say, more than the input voltage here in let's say in these connections. But something I realized when I was studying this like 10 years ago, actually in summer of 10 years ago or 12 years ago, I broke my knee. Then I spent a lot of time without, let's say, moving, so doing simulations on my own in my house. And then I realized that it's not the same if you have, let's say, the lagging leg here or the leading leg. And what that means. So let me move forward. So here, what we can see is that when you have these two legs in a phase shift, the way to move the energy from primary to secondary, or let's say, or to change the data cycle, is to change the delay between the leg 1 and leg A and leg B. So you can see here that in this case, the leg A has a delay respect to the leg B. So this is the way that we move, let's say, we change the data cycle. So what we realized, or what I realized, was that depending on which leg is delaying to respect to the other, you have different effects. So let's start for the option 1. The option 1 means that the lagging leg is the B. So what that means that here you have this behavioral, like you are having this conduction. This is the, let's say, the conduction here of the state A. And then at some point you switch off the Q1 and you have this situation here where you have the current through the resonant inductance introduced with the leakage inductance. And as you can see here in the current through the resonant inductor and the leakage inductance and the, let's say, transformer is a little bit different because you have some current flowing through the clamping diodes. So this is the current through the clamping diodes. But what happened if you change which leg is the leading and the lagging? So what's happened is that in the second part of the cycle, the current through the transformer and the current through the resonant inductor are not the same, because basically when the current is going to decrease in the transformer, that is the red line, then you are clamping the current through the resonant inductor. So you can see that the current flowing through this loop here is stable, let's say it's steady, until, let's say, we switch off Q1. So in this process, you have a different flowing of energy. And what that, let's say, the impact of that, and I'm going to try to move forward fast, is that here you can see the two cases. This is the case where you have, let's say, the option 1, where both currents are, let's say, equal, and then this is the other one when you have the difference between the leakage and the resonant. And what's happened is that you have different results. So, for example, for option 1, you have lower losses in the clamping diodes. So you can see in the option 1, the current in the clamping diodes is just this current. So coming back to this point here, you can see that the current through the clamping diodes is just this current. But in the option B, in the option B, you increase the 0 voltage switching range. Why? Because here, the effect of the 0 voltage switching is happening with the instant current that you have during this commutation. And the current here is higher in this case than in this case. So as you can see here, the current is this value, let's say, and in the option B is this value. So this difference of energy is increasing the range of 0 voltage switching. But of course, you are paying the taxes of the conduction losses in the clamping diodes. But what we can see in the comparison of the efficiency is that in the lower, let's say in the lighter loads, zero voltage switching has a lot of impact that, let's say, have more impact than the additional clamping diodes conduction losses. So it's more efficient to have the option be in the lower, let's say in the lighter loads. Depending on your case, you will need to make a trade-off because I don't like to have this current in the clamping diodes. I mean, it's too high, and this clamping diode is supposed to be very small and, let's say, very light. So you need to make sure that they are not going to exploit. But for lighter loads, you can win something here if you change from mode A to mode B. And before jumping to the questions, so let me remind you what is, let's say, our pricing for our platform. So we have the free part we call hobby. So you have up to 8 credits to do whatever you want to do in terms of design magnetics and converters. Also, we have, let's say, our launch of 100, actually this is 1,000. So 99 users per month where you can do whatever you want unlimited. And then if you want to jump to the simulator, also you can get just this month for $1,000 per users per month, the complete platform. So everything. So let us know if this is interesting for you. And now let's jump to the questions. Okay, so Marcus, help me a little bit with the questions. Let's see, for example, somebody say like, I suppose zero voltage, phase shift full bridge will not be efficient below 400 watts or even economically price versus power. What do you think?
Yeah, that's completely true. Because at the end, as you commented, Flyback maybe is more interesting at this range also because you need only one semiconductor and only one driver. And with the phases full bridge, you need more drivers and more contract techniques. So yes, yeah, it's true. It's more economical.
The only point is that I feel between 400 watts, and I wouldn't use a Flyback higher than 120, let's say. So from 120 to 400 watts, you have to be careful. So probably it's more maybe a half bridge or maybe a push pull. I don't know, but
yeah,
definitely something
yeah.
in between.
Yeah.
So there is another question: how you compare phase shift full bridge with resonance? So are, let's say, similar in terms of the number of components and everything, but there is kind of for me, and I don't know what you think, Marcus, but for me, it's more about complexity. So the LLC is much more complex for regulate, for controlling, and you're winning a little bit of efficiency, no?
Yes, true. In terms of efficiency, if you are operating at resonant, that's the best case scenario, and you have the maximum efficiency. But out of that, you need to be careful because the control is difficult.
So there is another question about if the system provide an idea of the air gap in the transformer. Yes, our system calculates the air gap, and if you are, let's say, the air gap usually for professional design should be in the center leg, but you can also get the air gap in the, let's say, in the 3 legs if you want. There is somebody asking if is the inductance value going to reduce if we are using a planar core? That's a good question. The inductance is going to reduce. So, you have to reduce because you cannot give as much turns as in a concentric. That's true. But if your tune ratio, let's say, is 4 or I don't know, more than 4, I don't know. What do you think, Marcos?
If I understand well the question, basically, yes, with planar shapes, you have less space, but in terms, depending of if you are using PCB or not. So, but the inductance at the end, it depends on the geometry of the core, not all, because at the end, if you have the same effective area, it is true that if it's low profile, it can be changed a bit the permeability, but if the same shape with more height or less height should we have the same level of inductance, not too much different, from my point of view.
I mean, in what I will say is that if you don't have too much current, this planar, and I mean a planar in this case could work. And of course, you need to have less turns because you have less space, and the way you have the turns can be a mess, and you will increase a lot the parasitic capacitance, which is affecting your zero voltage switching. Because in the zero voltage switching, the parasitic capacitance, you have that one as well. So
and from the other hand, you have less leakage inductance, so maybe you need to add an external inductor in order to help you, or reducing the magnetizing inductance until.
And this is where resonant converters make sense. If you, let's say, if you want to have just one magnetic component, even they are more difficult to use. But in this converter, we have to remember we have an output inductor. So we have transformer, output inductor, and maybe an resonant inductor. So the ideal would be avoid one of them, let's say, or integrate all of them. Actually, we have a pattern with that. But yeah. So so there is people asking for the adaptive control. Yeah, you can do adaptive control for this. Actually, you can change the dead time and everything once you're changing the power level, and I think there are some chips doing that very well. And also somebody's asking if what do you suggest to address that issue in terms of control, the light load losses. So in terms of control, there are one chip, 28580, I don't know. I mean, it's from Texas Instruments. It's a very, very classic chip. This chip, when you are in light load, you put a limit and the system start entering in burst mode. That means that it's going to be very kind of efficient in terms of not entering in a very crazy mode of losing, let's say, the power. But if
burst mode means you are skipping pulse.
Yeah, I mean, it's like a switching on and off the whole system all the time. So you are trying to just protect the system, but delivering power. In any case, if I would be dealing with that, I would try to negotiate which is the minimum power I need to deliver. Because the problem with the phase shift full bridge is in very light power, because you have, let's say, you have very low efficiency and you can have a lot of problem for switching losses. So I would try to negotiate. I mean, below 10%, I'm going to switch off myself. So not trying to deliver zero power. Actually, you cannot easily say like, I'm going to be on and delivering zero power. That is not going to work. You have a lot of circulating currents and crazy things. So yeah, somebody gave us the name of the chip. It's 28950. Yeah. So there are more questions. Please write us an email for those questions. We don't have time for more today. And the other point is to if somebody is asking for their slides, we will share the whole recording. So don't worry about that. If you have registered, you will get the whole recording. So thank you very much, and thank you, Marcos.
Thank you, Chema. Very interesting webinar.
Yeah. So talk to you next week. Bye-bye, guys. Thank you.
You too. Bye-bye.